Welcome to Bite-Sized Breakthroughs, where we dissect the latest research in AI. I'm your host, Alex Askwell. Today, we're diving deep into a fascinating paper titled Native Sparse Attention, Hardware-Aligned and Natively Trainable Sparse Attention. With us is Dr. Paige Turner, the lead researcher behind this work, and Professor Wid Spectrum, an expert in large language models.
Thanks for having me, Alex. It's a pleasure to be here. This is crucial work.
Dr. Turner, can you set the stage for us? Why is long context modeling such a hot topic, and what are the limitations of traditional attention mechanisms?
Absolutely. Long context modeling, or the ability for language models to process very long sequences of text, unlocks capabilities for reasoning, code generation, and complex interactions with AI agents. Think of models that can process entire code repositories, lengthy legal documents, or maintain coherent conversations over thousands of turns. The problem is that vanilla attention, the core mechanism in transformers, has quadratic complexity. This means the computational cost increases quadratically with the sequence length. For a 64K length sequence, attention can account for 70 to 80% of the total computational latency during decoding. To put it bluntly, it becomes incredibly slow and expensive.
So, the standard attention mechanism becomes a bottleneck. Professor Spectrum, what is the significance of this latency bottleneck, and how does it affect the broader field of LLMs?
The bottleneck is huge. It limits the scope of problems we can tackle with LLMs. For instance, complex, multi-stage reasoning or understanding very long documents becomes impractical due to the computational cost. It also increases the energy consumption and hardware requirements for these models, restricting accessibility and slowing down progress. Furthermore, as the context window increases, naive attention creates a very large KV cache. Managing that cache efficiently becomes a significant engineering challenge.
Dr. Turner, that brings us to sparse attention. What is it, and what are some of the existing approaches? What sets your approach, native sparse attention, apart?
Sparse attention aims to alleviate the computational burden by selectively computing attention scores for only the most important query key pairs. Instead of attending to every token in the context, you attend to a carefully chosen subset. There are existing methods like KV cache eviction, which discard less important keys and values, or blockwise KV cache selection, where you choose relevant blocks of keys and values. Other techniques use sampling, clustering, or hashing. But many of these methods are primarily focused on the inference stage, the point when the model is generating output, not the training stage. And that's a major problem. Also, many don't translate well to hardware acceleration. NSA is natively trainable. We designed it from the ground up to be trained with sparsity, meaning the model learns the sparse patterns during pre-training and optimized for modern hardware using blockwise sparse attention for tensor core utilization and memory access.
So, by natively trainable, you mean the sparsity pattern itself is learned during the training process, not applied after the fact?
Exactly. Many methods apply sparsity post-hoc, which forces the model to deviate from its originally optimized path. Chen et al., 2024, showed that even the top 20% of attention scores only cover about 70% of the total attention scores. So, simply pruning after pre-training can harm retrieval heads that depend on those pruned connections. By training with sparsity from the start, the model adapts and learns to compensate for the selective attention, maximizing its performance within the constraints of the sparsity pattern.
Professor Spectrum, what are the implications of training a sparse attention model from scratch, as opposed to applying sparsity later?
It's a paradigm shift. Training from scratch allows the model to learn the optimal sparse patterns, instead of being forced into a suboptimal sparse configuration after full attention pre-training. Furthermore, training is now significantly cheaper. We no longer need to do full attention pre-training, saving significant compute resources. Training a sparse attention model will result in very different emergent behavior and optimized internal representations compared to simply pruning a dense network.
Let's delve deeper into the NSA methodology, Dr. Turner. How does NSA work? Specifically, what is this hierarchical approach you've developed? What do token compression, token selection, and sliding windows do, and how do they work together?
NSA employs a dynamic hierarchical sparse strategy using a three-pronged approach. The main idea is to, given a query, replace the original key value pairs with a more information-dense set of key value pairs. The key value pairs are processed via compressed coarse-grained tokens, selectively retained fine-grained tokens, and a sliding window for local context. The first component is token compression. We aggregate sequential blocks of keys and values into block-level representations using a learned MLP. We compress L tokens into one, where L is the block length. The second component is token selection. Here, we selectively keep the most relevant tokens. We divide keys and values into blocks, then compute an importance score for each block based on the attention scores from the compression tokens. We then keep the top n most important blocks. The final component is a sliding window for local context. This is simply keeping a fixed size window of recent tokens, like the W most recent tokens. A learned gating mechanism combines the outputs of all three components. These components allow NSA to have coarse-grained information via compression, selectively kept fine-grained information, and local context.
Let's break that down further. For token compression, what is the trade-off between compression ratio and information loss? How do you choose the block length and stride?
That's a crucial consideration. A higher compression ratio means fewer computations but potentially more information loss. In our experiments, we found a block size L of 32 and a sliding stride D-tut of 16 to be effective. We use a stride of 16 rather than 32 to mitigate information fragmentation. The MLP inside the token compression block also adds positional information to the tokens inside the block to mitigate information loss. The specific optimal values will depend on the dataset and model size, but this setup seemed to achieve a good balance.
And for token selection, how do you ensure that the most relevant tokens are selected? What goes into importance score computation, and what are the benefits of blockwise token selection?
We leverage the attention scores from the compressed tokens to compute the importance scores. So we are not introducing additional parameters to calculate importance. We first softmax the query and compression key products to get the attention scores. We then aggregate attention scores within a selection block. Blockwise selection is important for hardware efficiency. Modern GPUs perform significantly better with contiguous block accesses than random index-based reads. By selecting blocks of tokens, we can maximize tensor core utilization. This is why we do not select individual tokens, but blocks of tokens. Prior work has also shown that attention scores often exhibit spatial continuity. If one token in a block is important, the neighboring tokens are likely important as well.
It sounds like the hardware alignment aspect is critical to realizing the theoretical benefits of sparsity. Professor Spectrum, can you elaborate on the challenges of translating algorithmic efficiency into actual hardware speedups?
That's a common pitfall in sparse computation. Many algorithms show promising theoretical speedups, but when implemented on real hardware, the overhead of managing sparsity, things like irregular memory access, thread divergence, and underutilization of computational units, can negate the benefits. Unless the algorithm is carefully designed with the underlying hardware architecture in mind, you won't see the expected speedups. Efficient use of GPU tensor cores and memory hierarchies is essential.
Dr. Turner, you mentioned NSA's kernel design. Can you describe the key features, such as group-centric data loading and shared KV fetching? How do these optimize memory access and arithmetic intensity?
Our kernel design is specifically tailored for grouped query attention, GQA, and multiple query attention, MQA architectures, which are becoming increasingly common in modern LLMs. These architectures reduce memory access by sharing the KV cache across multiple query heads. The core principle in our kernel is to load groups of queries into shared memory. Within the kernel, our first optimization is group-centric data loading. We load the queries from each group at position T and the shared key value block indices for each query head. Our second optimization is shared KV fetching. We then fetch each KV block, where each block is indexed by the group-centric loading into SRAM to minimize memory loading. In the outer loop, we're using Triton's grid scheduler to simplify the kernel.
So that ensures that the memory accesses are all nicely coalesced together.
Exactly. This minimizes redundant KV transfers and balances the compute workloads across GPU streaming multiprocessors, which maximizes arithmetic intensity.
Let's move on to the experiments. What data sets did you use? What were the key metrics? And what were the headline results?
We performed extensive evaluations across general benchmarks, long context evaluations, and chain of thought reasoning. For general performance, we used benchmarks like MMLU, BBH, GSM-8K, math, human eval, and others to measure knowledge, reasoning, and coding capabilities. For long context performance, we used the long bench benchmark and a needle in a haystack retrieval task with 64K context. Finally, for chain of thought reasoning, we used the American Invitational Mathematics Examination. Our key metrics were accuracy, F1 score, pass at 1 for coding, and retrieval accuracy for the needle in a haystack task. The main results were that NSA achieved superior overall performance, outperforming all baselines, including full attention on general benchmark metrics. NSA achieves perfect retrieval accuracy on the 64K context needle in a haystack task. On long bench, NSA had the highest average score, and it also achieved higher accuracy on the AMI under the 8K context setting. Finally, we saw a 9x forward speedup and 6x backward speedup compared to flash attention 2. We observed up to 11.6x speedup for decoding at 64K context length.
Impressive results. Can you elaborate on the comparison with full attention and the other sparse attention methods? What specific advantages did NSA demonstrate?
In general evaluations, NSA outperformed full attention on most benchmarks, even though it may not fully leverage its efficiency advantages on shorter sequences. But notably, NSA showed significant gains in reasoning-related benchmarks like DROP and GSM-8K. In long context evaluations, NSA outperformed all baselines, including full attention, H2O, InfLM, Quest, and Exact Top. It showed substantial improvements on multi-hop QA tasks requiring complex reasoning. And, as I said before, we saw substantial speedups in training and inference.
The needle in a haystack result is particularly striking. What explains NSA's perfect retrieval accuracy in that task?
That highlights the effectiveness of our hierarchical sparse attention design. The compression tokens provide efficient global context scanning, while the selection tokens ensure that the important details are preserved. By combining the compressed, coarse information with the selected fine-grained information, we maintain both global awareness and local precision, allowing us to perfectly find the needle.
Professor Spectrum, what is your assessment of these experimental results? Are there any aspects that stand out or require further investigation?
The results are certainly compelling. The ability to outperform full attention on some benchmarks suggests that sparsity, when learned correctly, can actually improve model performance, not just efficiency. The speedup numbers are also significant and could lead to real-world impact. However, it's important to remember that these results were obtained on a specific model size, 27B parameters and architecture, GQA plus MOE. Further investigation is needed to assess the generalizability of NSA to other models and datasets. Further benchmarks should be conducted in addition to the long bench benchmark.
Speaking of limitations, Dr. Turner, what are the key limitations of your current work and what are the next steps in your research?
One limitation is the generalizability of our results to other model sizes, architectures, and datasets. We need to explore how NSA performs with different models. While we achieved significant speedups, the exact performance gains may vary based on the hardware. We also focused on specific sparse attention patterns, and we could explore combining NSA with other sparse attention techniques. Finally, our long context evaluations were limited to specific tasks. We would like to perform additional evaluations on other long context datasets. For future directions, we want to explore hierarchical sparse attention strategies and explore techniques to learn more optimal sparse attention patterns. We also want to apply NSA to other modalities like vision or speech.
Let's zoom out a bit, Professor Spectrum. What are the broader potential applications and impacts of this work?
If NSA proves to be widely applicable, it could have a transformative impact. The ability to train and run long context models more efficiently would unlock new possibilities in many areas. Imagine more powerful AI assistants that can understand complex instructions, better models for scientific discovery that can analyze vast data sets, or even more realistic simulations that can process complex environments. In the long term, NSA could enable us to tackle problems that are currently intractable due to computational limitations. Also, lowering the training cost of long context models is essential to making the technology more widely accessible to the broader AI community.
Dr. Turner, any final thoughts on what you hope this work will contribute to the field?
I hope our work demonstrates that training sparse attention models from the ground up is not only feasible, but can also lead to significant improvements in both efficiency and performance. By combining algorithmic innovation with hardware awareness, we can unlock the full potential of sparse attention and pave the way for more powerful and accessible long context language models.
Dr. Turner and Professor Spectrum, thank you both for sharing your insights. Today we went deep into the world of native sparse attention, or NSA, and its implications for the future of AI. The discussion illuminated not only the novel hierarchical approach of NSA, with its token compression, selection, and sliding windows, but also the importance of hardware alignment and training-aware design. We found that this leads to faster and better long-context modeling. That's all for this episode of Bite-Sized Breakthroughs. Join us next time as we explore another exciting development in the world of AI.